Merci, Eric. All right. I don't think that's the first slide, though. Okay. Pouvez-vous remettre sur le premier transparent, parce que je ne peux pas retourner en arrière, apparemment. Mais c'est pas le premier, celui-là. Encore. Voilà, merci beaucoup. Okay, I'll switch to English. So towards autonomous machine intelligence, I'm going to talk a lot about self-supervised learning and the idea of learning world models. This is something that you already heard a bit about by Michal Valko yesterday, and you'll probably hear more today, I think. So you're going to see some parallels between the two talks. I'm going to focus more on particular aspects of this. First we start with something that we have to realize, which is that the current techniques that we have in machine learning suck. I mean, they're not very good, in the sense that when we see what animals and humans are capable of doing, how fast they can learn new tasks, we realize that the learning techniques that we have at our disposal at the moment are nowhere near what we observe in biology. And so we need to bridge that gap, because we'd like to build machines that are as intelligent as humans and animals to start with. So I made the point yesterday, and Michal also, supervised learning requires a large number of labeled samples. Reinforcement learning requires absolutely insane amounts of trials. It works for games because these are artificial environments, but it doesn't really work in the real world unless you use all kinds of tricks to kind of make it more efficient. The result is that systems that are trained with supervised or reinforcement learning are very specialized and brittle. They make stupid mistakes, and they do not reason nor plan. Whereas when we look at animals and humans, even fairly simple animals, they can learn new tasks really quickly. They have some understanding of how the world works around them. They can reason and plan. We don't think of a rat as being able to reason or plan, but they do. And they do fairly sophisticated planning, actually. And they do have some level of common sense that current machines really don't, including ChatGPT or anything you can think of. And that's really a limitation of AI systems since the beginning of AI, but it's becoming even more clear today. So don't be fooled by systems that you can hold a dialogue with. They really don't understand how the world works. And they are nowhere near having the right ingredient for human level or even animal level intelligence. Okay, so machine learning systems, most of them anyway, have a constant number of computational steps between inputs and outputs, including things like ChatGPT. So for ChatGPT to produce a word, it goes through something like 40 layers of transformers, and that's it. And it produces a word, and then that word is rejected on the input, and then it produces the next word, right? So there's no reasoning, there's no planning, it's completely reactive, and every production involves a finite number and fixed number of computational steps. Whereas when we reason and we plan, we can think about it for a long time before we actually figure out a solution. We imagine all kinds of scenarios, and then we figure out a sequence of actions that will satisfy an objective that we set ourselves. Systems like large language models, and I don't want to, I just say ChatGPT because everybody knows about it, but all large language models, and there is a whole bunch of them, they, pretty much all of them, almost all of them, are reactive. They don't do this type of reasoning and planning in advance. They don't really have well-defined tasks that they have to accomplish. The tasks that they accomplish are defined by the prompt that we furnish them, which is a very indirect way of specifying a task. So again, animals and humans understand the world. They can predict the consequences of their actions, and as a consequence, they can perform chains of reasoning to basically predict what sequence of actions will satisfy a particular objective. So how is it that humans and animals learn so quickly? So take a baby. Babies open their eyes and then learn about how the world works, basically by observation. By the age of just a couple months, they figured out the difference between animate and inanimate objects spontaneously. There's no language involved or anything. They figured out basic concepts like the world is three-dimensional, object permanence, so the fact that when an object is hidden behind another one, it still exists. They elaborate natural kind of categories. You don't have to tell them the name of objects. They know the difference between a chair and a table and something like that, or a car. And then by the age of 9 months or so, they start figuring out things like intuitive physics, the fact that objects are subject to gravity, they will fall if they are not supported, they have inertia, there are certain things that are heavy and that you can move and others that you can't. So this takes a long time, and it's mostly by observation. There is a little bit of interaction, but a three-month-old baby basically cannot influence the world. The only thing he can influence is his own position or configuration, but cannot really affect the world, right? So a lot of this is done purely by observation. If you show a 6-month or 5-month-old baby a scenario like the one at the bottom left, where you have a little car on a platform and you push the car off the platform and the car appears to float in the air, a 5-month-old baby will barely pay attention to it. A 10-month-old baby will really stare at it for a very long time, like the little girl at the bottom here, because she has learned about gravity. She knows that an object that is not supported is supposed to fall. And so her model of the world was violated, and so she kind of stares at the scenario with a lot of surprise to correct her world model. So how do we do this with machines? And the type of knowledge that we acquire as babies and that animals do similarly is the basis of what we call common sense. It's an enormous amount of background knowledge about how the world works. We don't have any system today, any AI system, that is capable of doing anything like that. Okay? So it's a challenge for all of you who want to get into AI research. Solve that problem. To solve that problem, you'll basically bring about the next revolution in AI. I'm not kidding. Okay, so 3 challenges, in fact, for AI and machine learning over the next decade is learning representations and predictive models of the world from observation, perhaps some video. And that will involve self-supervised learning and things like that. Learning to reason, so not have neural nets that just have a finite number of steps between input and output, but things that are capable of mulling over something. And then learning to plan complex action sequences, and possibly hierarchically. So I'm going to address how we could go about this, and some of it is kind of a projection of what we should be working on over the next 10 years, some of which, and we started working on some of those aspects, obviously, but this is going to take a while. And our friends at DeepMind are also working on similar things. There's people at Berkeley working on things that are somewhat similar, so or sort of with the same motivation. So I gave a somewhat technical talk about this at Berkeley a few months ago, which you can watch on YouTube, but it's going to be a repeat of what I'm going to talk about today, with one today has a bit more advanced results. And there's a long paper that I wrote, a position paper on where I think AI research should go over the next decade on Open Review. If you type Open Review, Yann Lecun, you'll find the paper. It's called A Path Towards Autonomous Machine Intelligence. It's a long paper, but it's fairly readable. It's designed to be readable by a lot of people from various backgrounds, including neuroscience and cognitive science. In that paper, I propose overall architecture, which I don't claim is particularly new, but it's a way to sort of make a little concrete various things that people have been kind of thinking of and working on. And the centerpiece of that architecture, let's go a cognitive architecture if you want, is the world model. So the world model in green here is a module in the system that allows the system to predict what's going to happen in the world, either because the world is evolving or as a consequence of its own actions. The system can imagine sequences of actions, and this is the role of the actor, the yellow box. So the actor proposes action sequences, feeds them to the world model, and the world model predicts what's going to happen as a consequence of those actions. Okay. It may use a memory for this to kind of figure out, previous conditions that were observed. The world model is initialized through perception. So the perception system basically gives you an idea of the initial state of the world so that you can make predictions for a future. And then the purpose of the entire system is to minimize a cost function. This is not a function that will be minimized by learning. This is a function that will be minimized by planning. Okay? So you have a cost function which determines an objective, a task that needs to be accomplished. And that cost function may have multiple terms in it that ensures the safety of the system, or various. So you have intrinsic costs that are things like don't get too close to open fire, or don't flare your arms if you are a robot and you have a knife in your hand and there are people around. Don't move too fast. Things like that. So you can put a lot of rules in the form of intrinsic costs inside that system to control it. And then one of the costs is going to be an objective. Park the car, whatever. Okay? And the entire purpose of the system is to figure out a sequence of action. It's for the actor to figure out a sequence of actions that, according to the world model, will minimize that cost so that you will accomplish the task. Now, from one time to the next, the system may have to change its objective, and that's going to be done by the configurator. So the module at the top, configurator, is going to configure the world model, the cost, and everything else, the perception, for the task at hand. Okay? And then once that task is accomplished, you can switch to another task, and that will be determined by this configurator. So once the actor has planned a sequence of action to accomplish a goal, it spits out the first action or the first few actions to the world, observes the result, and then plans again. That's called receding horizon planning in optimal control. Okay, so that's the general architecture. We can use it in a particular way that I call mode 2 by analogy with Daniel Kahneman's system 2. So Daniel Kahneman is a famous psychologist. He's actually a Nobel Prize laureate in economics, but he wrote this little book called Thinking Fast and Slow, and he explains that there are kind of two ways that humans and animals decide to act. One is kind of reactive. So you observe a situation and you immediately react. You don't have to kind of think about it and plan. So if you are an experienced driver, you don't need to plan to drive. You can do this subconsciously. Someone can talk to you. You can respond to them. It's kind of more or less automatic. But if you are an inexperienced driver, the first time you drive, your attention is entirely devoted to the task. Your consciousness is entirely focused on it. And so there you're using your planning engine. Okay, you're imagining scenarios, and then you're kind of planning actions that respond to those kind of imagined scenarios. So this mode 2, this is what Kahneman calls system 2. So mode 2 involves your model of the world. This is in the front part of your brain, if you want. And the way this would work in the model I proposed is this is the world model. It takes an action. It takes the initial state of the world and a proposed action, okay, and it predicts the next state of the world. And then again, here is the next action. Run the world model again, predict the next state of the world. Okay, so for a sequence of action, the system will predict a sequence of world states. And these are sort of abstract representation of the state of the world, if you want. And then those predicted state will go to the cost function. And the purpose of the system is to figure out a sequence of actions here that will minimize that cost. In optimal control, this is called model predictive control, MPC. It's very classical. It's the first examples of this were in the late 50s, early 60s, so it's a very old technique. Classically, the model of the world is not learned. It's handcrafted. Like you want to, plan the trajectory of a rocket to rendezvous with a space station. You have a precise physical model of the rocket, and you know what thrust and controls to apply, and your cost function here is how far you are from the space station, basically. Okay, so you can do this kind of planning. It's very classical in robotics. It's called motion planning. But the trick the questions we're going to ask here is, can we learn the world model by observation mostly? Maybe a little bit by interaction. So that's the kind of planning, right? So it's very different from like having a neural net where you put an input and then you produce an output reactively. This system actually does reasoning, okay? It has neural nets that predict things, but then you have to have this optimization procedure that figures out a sequence of actions that will minimize that cost, okay? There are AI systems today that use this kind of planning. Most of them are designed for games. So if you have a chess or Go player or some types of sort of deep learning-based control for robotics, they do have some planning. There's a system that was recently published and shown by my colleagues at FAIR called Cicero. It's a system that can play the strategy game diplomacy. And again, this system is capable of planning. So it's got this idea that you plan and you try to predict the consequences of your planning. And every Go and chess player board games do this by tree exploration or what's called Monte Carlo tree search. But here, I'm not specifying necessarily that this would be discrete actions. They could be continuous actions. And so we could use, if everything is differentiable, we can use gradient-based methods to figure out the optimal action sequence. Now, the cool thing about this is that if you have a system that's capable of doing this kind of planning, you can use the optimal actions that are predicted to train a policy network that just takes the state and directly predicts the correct action. This may not be possible in all cases. A system that plans is much more powerful, but in some cases, you might want to sort of compile a complex task that needs planning into a reactive policy. This is what happens when we learn to drive. So in the first few hours of driving, we use mode 2. We're very focused on the task. We plan, we imagine scenarios. But then after we become experienced drivers, it becomes subconscious and we don't need to plan anymore. And so that's this idea of transferring things from kind of planning, conscious planning, if you want, to kind of subconscious reactive actions. And there are systems that do this already in various contexts, mostly games. Okay, so the cost function has to be composed of multiple terms. Some terms, and I think Michal talked about this somewhat yesterday, where he was talking about intrinsic costs. So you have intrinsic costs. These are costs that are hardwired in the system, and they basically drive what the system will want to learn, and it's the limits of its behavior. So these are things that will measure, the equivalent of pain and hunger and things like that, right? And will limit the type of actions the system can take to make it safe, to guarantee its safety and things of that type. And then the trainable ones are things for tasks that are not easily defined by a cost that you can just program. Those costs, you have to learn them. In some contexts, this is called reward models, but in fact, it's nothing more than a trainable cost, okay? And the way you train those costs is that you train think of them as a neural net that takes the internal state of the system, predicted by the system, and observes the cost, the resulting cost, by perhaps observing other agents accomplishing a task, and then figuring out that if they do accomplish the task, that means their cost is low, and then kind of learning the cost indirectly. That's called sometimes inverse reinforcement learning or imitation learning. But we're going to try to make all of this differentiable so we can use gradient-based methods for this. Now, here is the thing, though. This is something that nobody knows how to do properly, or at least not combined with learning, and it's called hierarchical planning. So hierarchical planning is, imagine that you want to go from here to Paris, okay? You can decompose this objective. So your objective function is, what's my distance to Paris? Right now it's large. So you can decompose this into two subtasks. The first task is go to the airport, and the second task is catch an airplane to Paris. The first task, go to the airport itself, can be decomposed. So that's the cost of that is measured by your distance to the airport, right? So the first thing you need to do is go in the street and call a taxi somehow. Pick up your phone or whatever, or Uber, or I don't know, to get to the airport, or a friend to drive you. Then to do that, you have to stand up from your chair, get out of the building. To get out of your chair, you have to activate all your muscles, and all the way down to millisecond by millisecond muscle control. And all of that plan is informed by the local conditions, what obstacles you're encountering, and things like that. So this is the idea of hierarchical planning, where you have an overall task, and you decompose it into subtasks, and then, as you go down the level, you kind of plan the initial segment of each subtask, and that kind of allows you to act. So in robotics, hierarchical planning is very common, but the definition of what the levels are is hardwired, is defined by hand, is engineered. The problem that we need to fix here is, or to figure out, is how to train world models that by themselves figure out what the appropriate hierarchy of concepts are. And if you think about it, that's what convolutional nets and neural nets have been doing. Deep learning is the idea that when you do perception, the system automatically learns the appropriate intermediate representations of the input, whatever it is, let's say an image. Okay, so it learns the appropriate hierarchy of features. The question I'm asking here is, how do we do the same thing for action planning? How do we learn appropriate hierarchical representations for planning actions? And again, as far as I know, nobody knows how to do this today. It's a completely open question. Now, this is complicated by the fact that the world is not entirely deterministic. So you cannot exactly predict what's going to happen as a consequence of your actions, because the world is not completely predictable. So you're going to have to model this through latent variables, so variables that you're going to draw at random, or perhaps decide of their value in some other ways. And they will, depending on their value, they will determine different possible states, predictions of possible states using your world model. How to handle this is actually not simple. There's a lot of efforts devoted to handling uncertainty and control and reinforcement learning in particular. But you probably have to deal with this in some ways. So the way in the following, I'm going to talk about non-deterministic functions, is that I'm not going to assume that there is a probability distribution that we can compute. I'm just going to assume that the function that we're going to compute is deterministic, but it has an extra input that is some sort of random variable, okay? Some people call this the variable substitution trick, change of variable trick, but it's just a way of expressing a probabilistic function. You write a deterministic function, but one of its inputs is a random variable, and it makes the output random to some extent. So that's what I call Z here. Those Z's are the latent variables. Okay, so hierarchical planning with uncertainty is you start with an observation of the world, X, you run into an encoder, which is a perception system, let's say a vision system. It produces S0, which is an initial guess as to what the state of the world is. Perhaps you had some idea before in a memory, so you can combine the two. And then you run through a second encoder that computes a more abstract representation of the world state that allows you to make longer-term prediction. And then perhaps another encoder, encoder 2, that produces an even more abstract representation of the state of the world, and which allows you to make even longer prediction. So if I were to plan my entire trip from here to Paris, millisecond by millisecond, all my muscle control, I just wouldn't be able to do it. It's too complicated, and also it's inaccurate because I don't know what the conditions are going to be when I get in the street or at the airport. I can't predict everything. But if I represent the state of the world at an abstract enough level, like I need to go to the airport and catch a plane, okay, it's very abstract. I can't tell exactly at what time. I can't tell exactly in what position I'm going to be. What I'm going to have to get lunch before that or not, things like that, like I don't care. So I have an abstract representation, and that allows me to make long-term prediction, which says, by tonight I might be in Paris if I do it right, okay? Not being able to make accurate prediction. But then that task I can decompose into going to the airport and then getting up from my chair, and then, what muscle actions should I take, all the way down to kind of low-level controls. So that's what we don't know how to do, essentially, like how to train a system like this. And in my opinion, the next again, I'm repeating this, but the next step in AI will occur once we are able to figure this out. Train world models that can allow hierarchical planning. This will solve a big problem for those of you who have played with large language models and dialogue systems. This will solve a major issue that large language models have, which is that they make really stupid mistakes. They make statements about the world that don't make any sense because they don't know how the world works. And so if we had world models, those systems will have some level of common sense. If they were able to plan, they would be able to generate text that is consistent. But none of the systems today do this, which is why they are not so great. So how do we learn models of the world? So this is where self-supervised learning comes in. And I'm going to talk about a set of techniques, and I think you'll hear more from Michal about this. Self-supervised learning is predicting or modeling the dependency between different parts of an input, let's say a video. So you see a piece of a video, and you train a system to capture the dependency with the rest of the video that you don't see, but eventually the rest of the video is revealed. And so you can train the system to capture the dependency, and the system, if you train it on enough video, will figure out that there are objects that move, and they can move according to certain rules. And if the camera moves, the view of the world changes because it's three-dimensional, things like that, right? Very basic things. But the world is stochastic, so you can't just train a neural net to predict the next frames in a video. It doesn't work. In fact, here is an example. So what you see here, this column here, is a very simplified video. So this is an overview from the top of a camera looking at a highway, and the green rectangles are cars. And this is the output of a convolutional net that is trained to predict the next few frames in that video. And what you get is that it predicts very blurry frames, essentially, elongated cars that are kind of blurry. Same thing here, the predicted frames, which are the last two, are very blurry. So this is all the work. And that's because the system cannot predict exactly what's going to happen, so it predicts the average of all the possible outcomes, and that's a blurry image. So how do we solve that problem? The way to solve that problem is to use what I call a joint embedding architecture, or particularly a joint embedding predictive architecture. So this is, again, something that Michal talked about yesterday. So this is an architecture of this type where this is the part that you observe in the input. So so this would be the full video, if you want. Y would be the full video, and X would be a partial video that only shows the piece that are observed. So think about this as an entire video clip, and think about this as just the beginning of that video clip, for example, or maybe a few frames here and there. And you train that system to encode the 2 frames of the video into 2 representations, abstract representation SX and SY, and then simultaneously train a predictor to predict SY from SX. Okay? So what you're going to do is predict what's going to happen in the world, but you're not predicting pixels. You're predicting representations that are extracted by an encoder. And that makes a huge difference. That's what's called a joint embedding. Joint embedding means you take your 2 inputs, you embed them using neural nets or whatever, and then you do something in that space. You predict in that space. You don't predict pixels. Okay, that's the mistake that a lot of people have done in the past. That's called a JEPA, Joint Embedding Predictive Architecture. And this is by contrast with generative models. So a generative model takes an input and then predicts the output, if you want, directly, right? So the cost function here would measure some divergence between the predicted output and the original output. But in this output, there may be a lot of details that are completely irrelevant. Okay, so in your planning to go to the airport and the steps you're taking to get there, the texture of the wood on the ground is completely irrelevant. This is not something you want to predict because it's irrelevant. So, you're going to drive in your taxi or your car to the airport, and along the streets or the roads there will be trees, and the trees are going to move in the wind. And the details of how those leaves move is irrelevant to anything, basically. You don't want to be spending any kind of resources predicting that stuff. But that's what you would have to do if you had a generative model. You would have to predict all the details that occurs in the video. As a result, the video cannot be actually predicted, and the prediction would be blurry. So this is the solution, joint embedding predictive architectures, okay? So I'm going to argue against generative model in favor of those joint embedding predictive architectures. There's one issue with it. Oops. There's one issue with this approach, which is that you also have to drop the idea that you're going to do probabilistic modeling. Because what you're predicting here is not a distribution over y. Because to predict a distribution over y, you would have to invert this encoding function, which could be some gigantic neural net. So you're not going to be able to predict a distribution of y given x, okay? So you're going to abandon two pillars of machine learning. One is generative model, and the other one is probabilistic modeling. The only proper way to understand, the framework to understand this is called energy-based model, which I'll talk about next. But there are several types of joint embedding architectures. There is sort of simple ones. This used to be called Siamese net. So these are two encoders that are identical, and you just try to make their representation equal. So this could be, for example, two views of the same scene. You want the representation to be identical because the scenes contain the same objects. Some version where you have a predictor, but it's a deterministic predictor. And this is a predictor with a latent variable, so it's a non-deterministic predictor. Okay, and that's kind of the thing that eventually we want to use. Okay, but what about energy-based model? So energy-based model is the idea that the way you understand those systems is basically you think of them as computing an energy function, f of x, y, and that energy function is designed or trained to give low energy to observations of x and y pairs. Okay, so your training set is a bunch of x and y's, and you want to give low energy to the x and y's that you observe, and you want to give higher energy to everything else. The first part is real easy. If you have some big neural net inside of this, you can tweak the weights so that whenever you have a training sample, you make the energy computed by it as low as you can. But the difficult part is how do you make sure that the energy is higher outside? Okay, and here is why it's important. So this is a very simple example here of some two-dimensional energy function where x and y are both scalar. And your training samples are those blue spheres here. And that surface is kind of flexible. It's computed by some neural net, okay? If you're not careful, if what you do is you just try to minimize the energy of the blue dots, the data points, you just pull down on them, right? To do gradient descent, so that the parameters of this energy function are tuned in such a way that the function gives low energy to the training samples. It could become flat. That's called a collapse, okay? The collapse problem. People have realized this problem, way back in the early 90s, that this could be a problem. So you have two strategies to correct and to avoid collapse. The first one is very simple. You generate those green points outside the region of data, and you push them up. Those are called contrastive methods. Okay, all methods that generate extra points that are not data points and push their energy up are called contrastive methods. And then you have another set of techniques that I call regularized methods, and they consist in basically regularizing the function, the energy function, in such a way that the volume of space to which they can give low energy is limited or minimized. And so that when you push down the energy of the blue spheres, the other parts go up because you have a regularization term that minimizes the volume of stuff that can take low energy, okay? So you kind of shrink wrap the training set in low energy regions. So I used to be a big fan of this. In fact, I kind of invented them back in the early 90s for joint embedding architectures. But now I'm a big fan of this, and this is the same argument that Michal actually used yesterday. I think those non-contrastive methods are much more efficient, right? So imagine that you start with a region of low energy symbolized by this pink area here, and you have data points. Some data points are not being given low energy right now, and some regions are giving low energy even though they shouldn't. What you want eventually is the system to kind of give this type of energy function, and you can do this with contrastive methods, generating those green points, or you can do it by basically minimizing the volume of this pink area, okay, in some ways. Now, the issue with this is that the reason why I don't like contrastive methods anymore is because in high dimensional spaces, the number of those green points that you're going to have to generate, so you push up the energy in the proper way, grows exponentially with the dimension of the space. And so that seems doomed, okay? So that's one argument. And keep this in mind, because I'll show you something that contradicts this in the end. But so I'm much more in favor of this. At least I kind of was until recently. Okay, so I'm making 4 pretty horrible recommendations here for the future of AI. First one is abandon generative models, one of the pillars of machine learning. Abandon probabilistic modeling, because for joint embedding, you can't, it's useless. And we don't know how to parameterize probability distribution in high-dimensional spaces anyway. We don't have proper probability distributions over the space of all images. We have energy functions. We don't have probability distributions, because we can't normalize them. Abandon contrastive methods, and abandon reinforcement learning. And I'm going to make Michal not be happy here. Or at least minimize their use. I think the purpose of reinforcement learning should be to minimize the use of reinforcement learning because it's so inefficient, and replace it by optimal control, essentially. Okay, I don't expect you to read this because it's a long list, but it's basically a list of different methods that have been proposed more or less recently as to whether they are contrastive or non-contrastive. So basically, every Monte Carlo method, every maximum likelihood method that uses any kind of sampling is contrastive. Masked autoencoders, BERT-style training, so the way we train large language models, that's contrastive too. Okay, and it works in the case of NLP because contrastive methods work if your set of outputs is discrete or your representation is discrete. It doesn't work so well if your representation or your output space is continuous and high-dimensional. Which is why you see all those language models doing amazing stuff, but in computer vision, SSL has been much more difficult to make it work. So in regularized method, you have things like BYOL that Michal was talking about yesterday, Barlow Twins VicReg, which came out of my lab, variational autoencoders, and things like that. And for contrastive methods, you have a whole bunch of loss functions you can use. People very often only use the one at the top, but which is, I'm not going to explain, but it's basically a loss function that when you minimize it with respect to the parameters of the energy function, pushes down the energy of the training samples and pushes up the energy of contrastive samples, okay? In fact, probably the most popular one is something called InfoNCE, or neighborhood component analysis, or nose contrastive estimation. Those are all the same thing, and they're basically softmax, right? So log softmax. So you have some function that is going to have the effect of pushing down the energy of the good guy, which is at the top, and then pushing up the energy of the bad guys, which are at the bottom. Let me skip this for now. Okay, so now let's talk about joint embedding architectures. So this is the old way to do them, and they didn't appear in the last 10 or 15 years. The first examples of this, Siamese nets, that are trained contrastively are from 1993. I actually developed this at Bell Labs for doing things like signature verification. So you give 2 images of a signature from the same person, and you tell the system, train yourself so that the representation that is extracted is the same for those 2 signatures. And then you give 2 signatures of different people, or maybe of one person and then another person attempting to forge the signature of the first one. And then you tell the system to push those 2 representations away from each other so that they are different, so that now in the representation space, you can use the Euclidean distance as a way of measuring how similar the 2 inputs are. So those things, there's a paper in the 1990s about this that I published. I kind of revived the idea a little bit in the mid-2000s, 2005, 2006. There were a couple of papers at CVPR on this with my students. And then the whole idea kind of was revived because of the SimClear paper that Michal was talking about yesterday, that sort of revived the interest in contrastive methods for computer vision because they managed to kind of make this work more or less well for pre-training a computer vision system to get decent performance on the ImageNet dataset. So it attracted the attention of people this method, but they're really, really old. They are 30 years old, essentially. So the way you do this is that you train with a series of positive and negative samples. So these are positive samples. These are different views of the same image, basically, and contrastive samples that you have to generate somehow. And you train a system to minimize the distance between the outputs for two identical images, and then make the distance large enough when they are different. And then you chop off the top layer and use those internal representations as feature vectors that represent the image. You can stick a linear classifier or some classifier on top, and then train that supervised and see what performance you get. Okay, and so this is pre-trained on unlabeled data, and this is trained supervised. And the result is that this works really well, but I'm going to argue for those regularized methods. So regularized methods are methods in which you don't have contrastive samples. And you heard about BYOL yesterday, where the two networks have to share the weights in some way using exponential moving average. And then you have some cost function that you minimize that only involves positive samples. And there has to be some normalization and a predictor for this whole thing to work. I don't understand why it works and why it doesn't collapse. I don't know if, from the talk that Michal said yesterday, there's a few papers that attempt to explain, including some from there, actually, but I really don't understand why it works. And then there is other methods. So those two came from my lab, Vic Craig and Barlow twins, and they're based on the idea that you want to essentially maximize the information content of the representation while at the same time making those two representations as similar to each other for the samples that you train on. And maximizing the information content, some measure of information content prevents the whole thing from collapsing. So that's how you train a joint embedding architecture or a JEPA non-contrastively at a conceptual level. You feed it with a pair of two things that have some dependency between them. You run them to two encoders. They don't need to be identical. They don't need to share weights. And then you have two criteria here that try to maximize the information content in those things. And that's difficult because we don't know how to measure information content. Okay, and then that goes into a predictor, which may or may not have a latent variable. And that predictor tries to predict Sy from Sx. Okay, if we can train this, we not only have a system that can extract representations of the world, we also have a prediction model. If Y is the future and X is the past and present, then that system can predict what's going to happen in representation space. So we have the building block that we need for a world model, right? So the VCREG technique consists in measuring the information content in the representation by, ignore this for the time being, by basically measuring the covariance matrix of the output vectors over a batch or a segment of data, right? So if you run a bunch of samples through this encoder, you're going to get a matrix of output vectors. You compute the product of this matrix transposed by itself, and what you get is a covariance matrix that measures the correlation, pairwise correlations, between pairs of variables in those vectors, okay? So one is measuring the covariance terms, which are the diagonal terms of this matrix, this covariance matrix, and the other one is the off-diagonal terms, and then they measure the pairwise correlations, basically, between all those variables. What we're going to do is we're going to try to make those variances 1 or larger than 1. We're going to try to make those off-diagonal covariance terms 0, okay? So that our objective function is going to be that. And this is going to make the variables here decorrelated, not independent, unfortunately. But what we've shown is that if you plug an expander here, so this is a neural net that's going to be trained that takes Sx and perhaps expands its dimension or even keeps the same dimension, and you run this criterion here, this will have the effect of actually making the variable of Sx pairwise independent. And we have a proof that, mathematical proof that that's the case. Okay, you do this for both sides simultaneously, you minimize the prediction error, and if you have a latent variable, you also need to regularize this, but I'm not going to talk about that. And so this is this paper that I was mentioning. It's on arXiv. You have the reference here. It's by Grégoire Millalon. Randall Balestriero and me. And it's this proof that shows that using an expander, you're basically making variable pairwise independent as opposed to just decorrelated. So this works quite well. This is from a paper from a while back. And it compares favorably with a lot of other self-supervised methods. But I'm not going to bore you with all the details. It's basically in the same kind of top performing methods. And it's pretty good also for transfer tasks. So if you pre-train on distorted versions of the ImageNet dataset, essentially. And then you fine-tune the system by sticking a linear classifier on top and then training this on a particular task, like segmentation on the COCO dataset, for example, or detection. You get pretty good performance, but not wonderful. But again, it compares favorably with a lot of other methods. And the cool thing is that you don't need any normalization. You don't need to share the weights between the two networks. And you have some good idea of why it works, at least a better idea of why it works compared to BOAOL, for example, where I don't understand. Maybe some people do. So no need for weight sharing. It still works if you don't share the weights. Here is a refinement that was published at NeurIPS in December called VicReg-L. And this one has a latent variable. And the latent variable basically is the fact that the first neural net, the convolutional net, is going to produce a map of features representing feature vectors for local areas on the image. And what the predictor is going to try to do is essentially match the features at the top to the features at the bottom by displacing them, by allowing them to be kind of moved. Okay, so if the two images are, for example, different framing of the same scene, the features will move, and that predictor will allow some mapping between the two by minimizing with respect to a latent variable, which tries to find the best match. And this works quite well, and it works well in the sense that you can train the system to work simultaneously well for image recognition as well as image segmentation, which was not the case for the original VicReg version. So again, I'm not going to go through the details of this table, but those are segmentation task, and the performance is much better than if you use kind of standard VicReg. So and you get good performance on classification simultaneously. This is perhaps a better chart here. But what it shows you is that there is a trade-off. So depending on whether you use a criterion that drives the system towards doing a good job on segmentation or doing a good job on recognition, there's a trade-off. You can either do well on classification by having very invariant features, or do well on segmentation by having non-invariant features that can localize object. But you can't do both at the same time. Unless you are just about here, which is sort of the optimal thing where you tune the two criteria for recognition and segmentation, so you get a good trade-off between the two. And you get a decent trade-off with a fairly large net that does a good job both at classification and segmentation with a linear head. Here's another technique. It's very, very new. It just appeared on arXiv a few days ago, basically. It's called IJEPA, ImageJEPA. And it uses a different technique to prevent collapse based on distillation method, which is a little bit more similar to what BYOL does, but it's kind of much simpler in some ways. So you have a first encoder here that gets a big chunk of the image as input and produces representation. In the experiment here, we use a transformer, not a convolutional net, unlike in VicReg. And here you have a corrupted version of the same image where you basically only have kind of a small crop of it, if you want, and run it through the same network and produce predict representations for kind of various regions of this full image. And you don't train this network, so those two networks have shared weights. Okay, they're the same weights. And the output of this network is normalized. It doesn't get any gradient back. But basically, what happens here is that this network attempts to match the representation that only so this network only has partial information. It tries to compute representations of regions of the images that is it doesn't see by training itself to predict the representation produced by the other one here. Okay, and you can do this with sort of multiple regions simultaneously. And this works amazingly well. It's very fast. It learns very quickly, and it works much better than what's called MAE, which means masked autoencoder. So masked autoencoder is a fairly popular method that appeared recently also from my colleague at FAIR in California, and which is a generative model. So it tries to reconstruct patches using a transformer and masking the first layer of that transformer, basically. But this works better than MAE. It's faster to train, and it gives you better result in the end. In fact, that's a better chart for this. So for a particular architecture, what you get here is, the accuracy here on ImageNet linear evaluation, and then in the abscissa here is the amount of computation that is required to train that system. So this is MAE, and that's IJPA. And it works really well on ImageNet. You get something like 81%. The very interesting thing about this is that this does not require any prior knowledge really about the nature of the input, because the only data augmentation it uses is masking. And you compare this with methods like SimClear or VicReg or anything like that, Dino, which is from FAIR Paris. Those methods work well, but they require pretty sophisticated data augmentation for them to work. So things like transforming the image in various ways, changing the colors, blurring them, etc. That SimClear also uses, and so that is not knowledge-free. Whereas masking, you can apply masking to any kind of input data, and it works really well. So that's really very interesting because we can probably apply this to a lot of situations, and it's in fact to some extent we have. These are results that are obtained when you pre-train on ImageNet, but then you train the classifier with only 1% of the ImageNet with labels. Only 1% of the images have labels. And you still get something like 77%, which is pretty cool. Okay, I'm going to skip this because, these are examples of reconstructions or nearest neighbor reconstructions with IJPA, but I'm going to skip this in the interest of time. Now, here is the thing, though. Both methods, the BYOL, VicReg, blah, 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 and SimClear, SiameseNet, and others, are both contrastive. They're just contrastive in different dimensions. So if you think about the set of vectors that come out of one of the encoders, right? So it's a matrix, a bunch of vectors. What SimClear does is a contrastive method because you're trying to make the rows of that matrix different. Okay? If you have a positive sample, it's 2 rows in that matrix, you're trying to make them the same. But then for contrastive samples, you're trying to make the rows, the representation vectors for those contrastive samples different from each other. Okay? So it's contrastive in that dimension. If you think about VicReg, VicReg tries to decorrelate the individual variables in the representation vectors. And what that means is that over a batch in this matrix, you're trying to make the columns of this matrix different. Okay? Now, here is the thing, and this is what this paper is about. And again, it's very recent. If you take that matrix and you compute that matrix times its transpose, okay, you get a particular covariance matrix. Or if you take that matrix transpose and multiply it by itself, you get another covariance matrix. Right? Those 2 matrices have very similar spectra and eigenvectors. In fact, the same, more or less. And so if you have a method that tries to make those matrices look like the identity, they basically are accomplishing the same work. And so that's an argument that says there's no real difference conceptually between contrastive and non-contrastive method. One set is contrastive over rows of a matrix, the other one over columns, but in fact there is some equivalence between those 2 things. And so this is the purpose of this paper. And to tell you the truth, I was really kind of very surprised by this result by Quentin Garrido, who was one of my PhD students at FAIR Paris, a resident PhD student, because I thought there was like an intrinsic superiority of non-contrastive methods. And this paper kind of puts this in question. So I spent the whole talk arguing for non-contrastive method, and then I'm telling you now, they're actually the same. It looks a bit disappointing. I don't think we understand everything about this yet. So we're still kind of in the process of figuring this out. but it's sort of an interesting question. And what Quentin managed to do is to actually tune SimClear and VicReg in such a way that they both perform as well as possible, and they get the same performance if you do it right on ImageNet, okay? May not be the case for other tasks, but for this, it clearly is. This is what those curves are. I'm not going to go through the details, but that's what those curves are showing. Okay, so hopefully we're going to be able to train JPAs in the future on generic videos. You know, we're getting close to this. And then perhaps we're going to be able to train hierarchical JPAs so that we can use them as hierarchical world models with which we're going to be able to do hierarchical planning. So, you know, that's a JPA, and it can do short-term prediction in sort of low-level abstract representations. Run this through another encoder, you get a more abstract representation here. Run this through a predictor, and perhaps you can make longer-term prediction with that. And so that you can do planning at that level, figure out an action here that will satisfy your cost function at that level, and then send that to the bottom level for hierarchical planning. So this is the model that would be used in a sort of mode 2 type hierarchical planning, which I was explaining at the beginning. So you have an overall cost function here, which basically is the cost that the task should minimize. You should minimize to accomplish the task. This is how far you are from Paris, essentially. Measures how far you are from Paris. You might need to learn that function because you need a way of mapping this abstract internal state to how far you are from Paris, okay? But that's okay. Not an issue. You can do this supervised by observing other people. Okay, so that will tell you the first action here is going to the airport and catching a plane to Paris, all right? How do I go to the airport? Well, this distance here, this cost function may indicate how far you are from Marrakesh airport. And that defines the low-level tasks for the bottom layer of, you know, I should get out of this building, catch a taxi to the airport, or get my friend to drive me or something, okay? And then, you know, you could go down the layers until you go down to sort of muscle control, but just this 2-layer would be great. So if we could just learn this hierarchical model simultaneously, that would be ideal. And then the circle would be complete. We would be able to integrate this into a cognitive architecture of this type, where self-supervised learning would play a critical role. Uncertainty would be handled through this latent variable, which I didn't talk about too much. And we could learn models from observation, perhaps observing other agents. And the system would be able to do planning and reasoning because that's how they are designed to operate. And I think this is a good model also for things like dialogue systems and question answering system. If they are capable of planning, if they have an idea of how the world works, if they have cost function that guarantees that what they're saying is factually correct, then they won't have the issues that current things like ChatGPT have, where they say very stupid things sometimes. In fact, most of the time. And then the configurator would be something that we don't really know how to build that would configure the system to solving tasks, you know, one after the other, and set sub-goals and things of that type. There's kind of a hypothesis here, which is that this may be a model according to which the human brain and the brains of animals is built. In particular, the fact that we may have a configurator and we probably have a single world model engine in our head. Why do we have a single world model engine in our head? Well, a symptom of this is that we can only accomplish a single conscious task at any one time. If we need to use our world model to predict stuff, we can't use it for anything else. Any task that we do consciously, we can do one task at a time. We can do a lot of subconscious tasks simultaneously. But the thing we do consciously, we can only do one at a time. And that suggests the idea that we only have one world model. But because we can accomplish lots of different tasks of a very different nature, what that means is that our world model is configurable for the situation at hand. And that's the role of this configurator. So this is what determines the function that we are focusing on at the moment, configures our world model for the situation at hand. And you would think, like, why do we have a single world model? We could have multiple. We would need much bigger brains. And also, we wouldn't be able to share knowledge between different configurations of the world model. Every situation we imagine basically are in the physical world or something related to this. So the different configurations of a world model has to share knowledge between the configurations, and that's why we have only one. We're smarter this way. For a given size of a brain case, if you want, it makes us smarter. This may be possibly, that's kind of a crazy hypothesis, but this could be an explanation for the illusion of consciousness. So the reason why perhaps we have consciousness is because we need to have this configurator that basically watches over the function of the other things. And that sort of gives the impression that there is this thing above the rest of the brain that controls it, right? Finding a general recipe for training hierarchical JEPA, I think, is a big challenge for the next few years. Designing surrogate cost that drives the hierarchical JEPA to learn relevant representations for relevant tasks is also a challenge. Integrating HJEPA into agent capable of planning and reasoning is a challenge. Devising inference procedure for planning in the presence of uncertainty using either gradient-based method or beam search or NCTS, Monte Carlo tree search. And as much as possible, minimize the use of reinforcement learning because it's so inefficient. So use trainable objectives, use planning, model predictive control, but only use RL when either your model or your objective doesn't match, doesn't do what you want. And that should be used as little as possible because any action you take in the world can kill you and also is very expensive, okay? So the reason why we can learn to drive a car in 20 hours without causing any accident is because we don't actually use reinforcement learning at all. Right. So when I say this to my friends at DeepMind, they're not happy, but that's what I think. Okay, thank you very much. We're very late, I'm sorry. Yeah, very good question. Yeah, okay, so should we, to repeat the question, should we incorporate prior knowledge in those world model, like gravity, the three-dimensionality of the world, you know, some elementary physics, perhaps, things like that, or should we train those systems from scratch? I'd say train them from scratch. And the reason I'm saying this is that for two reasons. The first thing is that learning those basic concepts, I think, are not that hard. It's not that hard. Learning that the world is three-dimensional is actually quite easy in a way, because if you train a system, if you take two pictures of the scene here, one picture here, one picture by moving your head 20 centimeters in one direction, or maybe two pictures from your two eyes, and you train the system to predict what the world is going to look like from here as a function of what it looks like from here, you're going to learn really quickly that the best way to explain this is that every pixel has a depth, right? Because that's the way to explain parallax motion. And so the notion that the world is three-dimensional, in my opinion, can be learned in minutes. You don't need to hardwire that in. And then the second problem is that we wouldn't know how to hardwire this in. If we use some sort of convnet or transformer, like what are you going to do? How are you going to wire the system so that it knows that the world is three-dimensional? It's not clear to me. Are you going to hack the representation? I'd rather have something that learned this. I had the exact same question way back in the first days of convolutional nets when I was, training LeNet or something. I was showing the weights in the first layer. And people, in computer vision and signal processing were telling me, like, why do you learn the first layer weights? We know what they should be. They should be oriented edge detectors. And I said, why should I hardwire them in? They get trained by themselves. Like, I don't need to hardwire them in. It's not any more complicated. If I have a rule to train all the layers in my system, I might as well train the first layer. And in fact, I tried the experiment of hardwiring the first layer with oriented edges. It doesn't work as well. So it trains faster, okay, with fewer samples, but in the end, it doesn't work as well. So I'm more a proponent of basically minimizing the amount of prior knowledge, but you had to have some, and the prior knowledge you need is things that are represented by the architecture of convolutional nets and transformers. My favorite architecture for vision is something called DETR, which I briefly showed yesterday, where you have a front end that is convolutional, and then the top, where you need to do like object-based processing, would be a transformer.
So thank you, Doctor, for your talk. And I have just one question. In the perception planning cycle, we have a cost function. So should we update this cost function as well in the process of the chicken actions as like humans? I think we have a cost function for each action. So in this cycle, should we update this cost in the learning process? Thank you.
Okay, so I went pretty fast on this, but the cost function that I showed is a cost function that is used for inference, not for training. Okay, so it's a cost function that is minimized by the inference procedure that figures out the sequence of actions to arrive at the objective, and whether you arrive at the objective is measured by this cost function. It's like an energy function. But the cost function that's minimized by training is something else, right? Now, that cost function, I said, should probably be trained because, again, if your plan is to go to Paris, the cost function should measure your distance to Paris. But then how do you measure this, given that you have to measure it from the internal state of your world model? And you don't know a priori what your world model is going to represent. It could be representing your position. Of course it should, but you don't know how. So you're going to have to train some sort of mapping to compute the cost function from the internal representation that your world model is predicting. And then you can do this by observation. So if you know what distance you are from Paris, from Google Map or whatever, you can train your internal cost measurement to compute that distance from your internal representation that will tell you if I'm in Marrakesh, I'm not in Paris. I'm, a couple of thousand kilometers from it. So you have to train that. Now, so training cost functions like this is known in the context of control as inverse reinforcement learning or imitation learning. So you basically observe another agent accomplishing a task, and you assume that the trajectories that the other agent is employing have low energy, have low cost, and you assume that everything else has higher cost. That's one way to train a cost function. But here, I'm separating the world model from the cost, and so it makes the problem of learning the cost much simpler. But what might happen at some point is that your idea of the cost was wrong. So, for example, you're riding a bike, and your idea of the cost function of whether you're going to fall or not is like how sideways you are or something. And you might fall because you thought you took all the right actions, but your cost function, your idea of whether you're going to fall or not, was wrong. Because, for example, you drove over a little rock, and it sort of destabilized you, and you fell. So that means your cost function was wrong. You didn't expect, or maybe your world model was wrong, but perhaps it was your cost function. And so you need to adjust either your world model or your cost function so that next time around you can make the right prediction and avoid the rock. And that's where reinforcement learning comes in, essentially. But that should be rare. Okay? In fact, we rarely fall when we ride a bike for that reason, because we have a good world model.
Next speaker, Michal. Valko, so it's like we have dueling networks today. Huh? It's like from DeepMind, also we tell different stories where RL is very important, and MCTS and Valko.Research solve many, many problems. Okay, so Michal, I'll leave you the floor.
Hello, welcome back. I'll continue of the talk that I started yesterday, and I'll talk about how actually we learn these world models, and Yann described in one particular way using the paradigm BYOL that I described, and then I talk a little bit of the theory after. All right, so just a little bit of recap what we have. I motivated why we would like to do reinforcement learning. One of the important things is self-supervised learning as a building block for it, because as Yann been drilling for a while, it's extremely inefficient to do reinforcement learning. And what we have today, it's like how to actually we learn the world model, particularly how we use them for exploration, how we encode the interesting motivation using the tools we learned yesterday. So I still did not abandon completely reinforcement learning, and I'm not planning to. But I cannot disagree with what Yann is saying with that it's extremely inefficient, and thinking that you can always just plan an agent and do tabula rasa from just very beginning and do some interesting behavior very fast. It's not the way to go. However, I believe that, for example, in science, we usually try to isolate, different effects. And, like, for example, in this particular situation, I'd like to isolate the scientific problems of, open feedback loops and closed feedback loops and picking the actions. However, if you would like to deploy the system, of course, you try to fill it with the world models, with potentially with some knowledge that you have, right? And then do only action in the past. But if you're, for example, learning them, and we try to understand what are the effects of the prior knowledge versus what are the effects of these interactions, it's also interesting to study interactions from the scratch. But even to actually find some world model that you would implant to the agent, that's actually still an open problem. How to do that well, and this is something that I will talk about, how to describe it. All right, so that's a plan for today. Yes, all right, just a little recap, what we will particularly use, because we still focus on one particular specific architecture over the 2 days, BYOL, so I'll recap the main intuition. For the vision, we had some source image, we did some potentially different, slightly different perturbations. We learned an encoder on the top, which in our case was convolutional net, some MLP that does a prediction, and then we regress to the targets. So when we do the learning, we backpropagate the weight, but since here's a stop gradient, we don't backpropagate the weight here. What we do instead, we copy the weights, from time to time, or do exponential moving average over the weights of the network before to get better targets and then get a better corner. After that, we output the encoder. So more specifically, what we do architecturally, we have a ResNet. So we would like to have something that outputs, in particular, in this case, 2048 numbers. So 2048 numbers is very good for representation. However, it's much easier to learn predictor with smaller number of features, so we project it to the smaller space, 256. We could also output 256, but that's too little and not rich enough as a representation. So we do both things on the online level and the target level. On the top of that, we learn a predictor, which is another NLP, and we just do a simple L2 loss, which, since we normalize the output, it's equivalent to cosine similarity loss. This is all that we can do, and we'll use this, throughout the next hour for our world models. All right. So why and how we would like to do the exploration of the world models. So let's back to these reinforcement learning paradigms that we know. You have some agent. You have learn well how to click. interacts with an environment, an agent can take some action and get some observation back. Based on observation, it can improve its action and its policy. And so in reinforcement learning, traditionally, we thought that outcome of reinforcement learning is a policy set. In every observation, what do you get as an output, right? So that's one way how agent can demonstrate and understand the world, so it can act in it optimally. But another way how agent can demonstrate it understood the world is to learn the world model, right? So the output of reinforcement learning can be either a policy or the world model or the both. For today, and it has been also focused on that, is about how to actually learn the world model. So we try to have some kind of deep network that, giving certain observation and action can predict kind of what happened next, or representation of what happened next. All right, so this is particularly important in this visually complex environment where we don't see everything, we don't have a map of everything, we just have some first view, we don't see what's happened behind us, we kind of need to remember it, and it's very hard to, we kind of would like to create somehow, ideally would try to create some kind of a map in our head so we can plan with this. And so we will try to focus on this kind of environment and build a world model for this kind of environments that we have here. All right, so our aim here will be to kind of encode curiosity. This is one thing that human does, it's one of, let's say, interesting motivation that we have, and it can empower the agents to learn a better world model because it can try to be curious about things it doesn't understand and go or observe things that it cannot explain. And we would like to have one agent that's effective across many domains, right? So for that, we have the extension or application of BYL for exploration that we call BYL Explore. All right, so as I was trying to motivate, exploration is an important part of reinforcement learning, and it's especially important when you have very sparse rewards. So this is, one, we have this kind of difficult environment, DeepMind or DM Lab 30, and from that we have hard exploration tags like DM Hard 8, and in that case, reward is extremely sparse. You get it when you get this apple, this golden apple behind the fence, and sometimes you don't even see it, so you need to get there. It's especially important when you have this sparse reward. But as we scale up to larger and more complex environment, it becomes completely infeasible. Try to explore everything in those environments. Yes. Next. So it becomes super crucial to pick what kind of things we will explore and what kind of things we'll just never do. And for that, we kind of learn the world model. So we have kind of 3 ingredients. We will have this curiosity-driven exploration, trying to be curious about things, how things works. We learn the world model, and then we reward the agents for fooling the model. I'll explain this in detail. Then we use we will never predict anything in a pixel space. So Yann already explained why this doesn't work very well. So we instead learn everything in a latent space, in an observation space. In appropriate latent space that we learn, so it should encode also some kind of dynamics. And, main thing will be the stuff that I re-described in the beginning of BYOL. So to jointly learn latent space and the world model. All right, so in order to pick and choose what we explore, we did this curiosity-driven exploration. So we built some kind of world model, some neural network. And then, this will be the first step, and then we use the mistakes of the world model to explore in other words, we go to the places where the mistakes is the larger, right? So we have some world model, has some policy, and then we try to go to the places, so we see where is the maximum mistakes of this particular policy, and we send the agent there. Go there where you cannot predict well what will happen next. So this model completely determines what is interesting and what to ignore. So a little bit more specifically, so we use BYL Explore as this latent world model. So we have this Latent world model first, so we particularly use this in RL settings, so we want to kind of account for this, sequence observations and some kind of the past. So we build up on BIOL and extend it to RL, so settings, because it learns kind of powerful dynamics model. So on the top of the images that we have, we also encode we also want to encode dynamics. So first, we have some kind of latent models of state, then we pass it through some kind of latent, we kind of get the latent observation. So this combination results in mistakes that are dynamics aware, and I'll describe specific architecture next slide. It will be much more clear, and also structured, because we are learning in the latent space. So we learn a latent representation that we can capture more abstract features that can be robust to the noise, because that's another thing that we want. Robust to the noise particular pixel space. So these result in a single unified objective. So it is the same objective that I described in the last slide, just most particular. We'll try to minimize the bio loss. So we try to find the best possible world model. So the model that we can explain the world the best, but then we maximize, we send the agents to the place where the mistakes is higher, right? So it's a min-max problem. And so the first part is, this encodes dynamics of the learning, and the second, somehow ask or implements exploration. Go to the places where you cannot explain what is happening. All right, so the mistakes that we have are somehow dynamics aware and structured, because they're on this latent space. So let's have some specific example of this, just very basic. So in practice, how this works, right? We usually implement this in on a cluster. So we have actors that implements the policy and create the trajectories, state observation, next state. Create a trajectory of observation, put them in some replay buffer, and then we have learners that takes this trajectory of observations and do some kind of learning to improve the policy. So we kind of, for example, at the beginning we don't know anything, and so we have some kind of random trajectories, and in these particular trajectories we have trajectories when we encounter the key, table, chair, and then unlocked lock and the apple, right? So we start this trajectory experience, seeing these various observations, and then we apply online encoder to embed this current sub-trajectory. So it's not only embedding ideally just thing, but the sub-trajectories all the way up till here of the same encoder, and also the future observation, right? So you already may see the similarity with the BIOL, and then it will be some kind of recurrent neural network, and from that we have some kind of belief states. From which this belief state will try to predict, the next future observation, right? So we predict the latent future observation from this current history, and again use this loss to train our predictor and our online encoder. So we use the same loss as intrinsic reward for the observation. Right, so I'll go about the specific architecture, but in high level, this is what we're trying to do. So this loss, so how bad we are, we use as intrinsic reward. We don't propagate, from the RL agent back to the losses. So we just create this intrinsic reward. So this is kind of non-differentiable part of it, at least for now. And send the agents when we get the biggest mistakes. All right, so now let's talk about specific thing, what we do. So I'll take example of Atari. So in this case, you have, this is one of the Atari games called Montezuma Revenge. These are the particular frames, the screens that we have that you embed in through the encoder, which is shared. You get the latent representation, ZT minus 1 over ZT. You pass the circle, there is RNN, you get to the belief states. So we call this part of the closed loop because there are kind of no actions in this. And now in the world model, we're kind of trying to plan in the head. So what would happen if that's we actually know what happened in the past. So we ask when we have the open loop part of it, we also add the action to our RNN, and we try to get the beliefs. So next action, what is the belief that is happening right now? Another action, recurrent neural network. So the next state, what is the belief already now? And from that belief, we try to predict, the next latent observation. So these will serve as targets. So remember in BYOL on the bottom, we had some target which was kind of the different perturbation of the original image. So this is kind of similar in the spirit. So these are future observations, and so this we create a target and we try to train the network, right? So for the target network that we have here, we take also the frames in the future because we know what's happening in the future. We pass it to the shared observation. Now we don't pass it through the recurrent norm state, and this is the target we will train, right? So this part, there will be stop gradient. This again will be some old version of the target encoder, right? So and again, as in BBIL, we use the L12. So we'll try to create some targets which are the embedded, so latent future observation, and we try to predict these latent future observation through our encoder and our RNN, right? So the gradient will flow this way through the trainable parts, which is the open loop and closed loop neural network and the encoder, and this here it will be untrainable, but we use again this exponential moving average to get the gradients. So this is particular how we will use the BYOL Explore in our example. All right. So how does it work? So we did the experiments on Atari as we do usually in DeepMind, and now we wanted to test how does it work in this visually complex environment. So these are Hard-8 exploration problems, which is three-dimensional. They're partially observable. They're stochastic, and you potentially have a multitask. I'll have some videos if it will work here. So one of the tasks, it's all called throw across. You have an agent, that's here and needs to kind of throw across, a ball on the other side. Either throw across, but usually it sometimes hacks the rewards and finds out it can just go or roll it around the board. And so you have a different view. So the only thing that the agent sees is this first-person view. Here we will see some kind of following the agent, and I think this video will not work, but I think I'll have some animation later. And this is a top-down view. This is what was actually happening, but this is not what agent sees, right? The agent only sees the first-person view, and that's why it's partially observable and difficult, right? So the agent sees something like that. This is another, one other task. You need to take this ball and move it to some other part. And so BYOL Explorer solves 5.5 or out of 8 tasks, where the previous the best result needed to have human demonstration, right? So here there is no human demonstration that were used. The expert demonstration, you just have this final reward, and without this human demonstration, the prior work they didn't even take off. They stay here, and we were able to solve, let's say, up to 6 of this hard DM Hard-8 task, right? And so we also did experiments on Atari and achieved this near superhuman performance on the 10 hardest exploration cases. So the other methods are the typical the action prediction, intrinsic curiosity model. The one of the most typical baselines is R&D and so on. And of course, what is interesting to mention that here we didn't need to use a lot of tricks that are used to make this method work. So, for example, when you have this extrinsic reward, so when you actually solve the task, and the intrinsic reward, usually the way how you combine and you just sum them together. But there is often different very sophisticated embedding mechanism to choose the reward that you need to tune. You need to add episodic memory and so on, and you can combine short-term and long-term words. And so we don't need to have any of this in the BYOL Explorer. framework. So another thing that, that we'll try to talk about next is that predicting next state is very nice, but it's very susceptible to stochastic reward, right? Like the most typical, example in the field is called noisy TV. When you try to predict the next state or next even latent state, and you have something like a noise in a TV or something that produces the noise, that agent just goes to the noise and gets attracted to it, right? Like because we send the agent where the mistakes are the highest. And so the mistakes are highest when you have like the pure, pure white noise, and you don't know what to predict it, so you always get rewarded for getting the going there. And so what ends up happening? The agent goes to in front of the TV, stares in front of the noisy TV, and never does anything interesting. So that's kind of the failure mode of this method. What is interesting to mention here that, like for example, in this kind of white noise, so we added just random pixels to the right state, and it was not perturbed. Our Biol Explorer some kind of was not perturbed by it, right? So the potential explanation is that the encoder was some kind of able to abstract and ignore the right part of it. So it's not particular. We don't particularly aim for this to solve this problem in this setting, but we were able to deal with some kind of noise. But in the next, I will talk about how to be more robust to the noise in general. All right. So I think there's just one video. Probably will, if it starts on this. If not, you can see them. They're all linked in a paper. So these are comparison against standard baselines, as I said. And I'll summarize this part. So like Biol Explorer is like one simple curiosity-driven algorithm that simultaneously does representation learning, dynamics modeling, and exploration, right? And so, we have a paper out that you can see from the detail. But now I'll actually talk specifically about these stochastic traps, or being trying to be robust to the noise in the environment. All right, and like the work that I'll describe, we call it curiosity in hindsight. So let's take this example that I described, the Montezuma Revenge, right, which is some kind of Atari game when you have an avatar, and you move to the different games, and it's very difficult exploration games. And one of the way how you can measure exploration is number of the rooms that you visit, right? So either we have more pure intrinsic, so we don't even give it a reward at the end. And R&D is like the typical baseline, which is something that you try to predict, the outputs of the random network, which and use this as interesting motivation. And Biol Explorer that does much well. And you can also combine extrinsic, so the true score. Let's say you get in Atari game and interesting motivation, and Biol Explorer does very well. So this is very nice. But if you just add some kind of stochasticity, and one easy way to add stochasticity, we call them with add sticky actions to the game. So this is something basic in this field. When you just try to play Atari, when you do action with some probability, you actually execute the action that you want, and with some other probability, you keep repeating the old action. That's why it's called sticky. And so there's some kind of randomness, because what you actually end up doing is not what you let's say what you wanted to do or what your policy wanted to do. What you click, let's say you click up, and then you click left, but you still go 10 times up before you actually before you go left, for example. So this is one of the sticky action. You can adjust the probability of stickiness. So if you add the sticky action to the Biol Explorer, R&D doesn't change that much performance, but the Biol Explorer completely breaks. So see from the top down, it suddenly doesn't even take off. Here it takes off a little bit. It has some kind of signal from extrinsic exploration. But for intrinsic exploration, nothing happens, right? So this is kind of the problem, because for a human, this is not a problem at all. To solve Atari or play Atari well with sticky actions. You just try this as a little kid. bump this key many, many times. And so next I'll describe the method is able to improve this Biol Explorer. So it will be kind of plug-in modification of the Biol Explorer that is able to deal with stochasticity of the environment. And so it's able to do it both, so when you have no randomness, so you would like to have no change in the performance. When you have some randomness, you would like to do still very well. And so this is what happens in our method. All right, yes, so this is, and so I always had two graph. One was like the same things goes for episodic score, because on the other things I was just showing number of rooms visited, which is kind of proxy for exploration, but same does, you can say, okay, I don't care about number of visited, I care about the score, but the same story works for score. So Biol Explorer, doesn't do well, but hindsight improves, over the Biol Explorer for both sticky action and, non-sticky, let's say, you can call them almost deterministic environments. All right, so I will first describe this conceptual framework, which augments this any prediction based exploration. I'll focus this on Biol Explorer because this is what we do, but any prediction based exploration could be used as an example. Second, I'll describe this practical implementation, particularly for as a drawbit modification of any of these methods. And finally, I'll describe some experiments that we did to show that this is robust, not just for sticky action noise, for a lot of different kinds of noises. Right? So this is not the first work that tries to deal with some curiosity-driven exploration. There is always some kind of prediction inputs and prediction targets, right? In some kind of, I think a lot of them would fit Yann's JPA style. So there is, the methods differ. I will not go to the details, but methods differ into, what kind of things goes in input and what kinds of go prediction output, right? And, there's different kinds of losses that predict, but there's also different kinds of noises this can be robust, right? Because the noise could be completely random, so you just add, random pixels to it. It could be dependent on the action, as an example of sticky action. It can be dependent on the state. They can have dynamic awareness. Some of them, predict directly in the pixel space. Some of them, do some bootstrap representation. So our method will work for any representation, and it will be, hopefully robust for all kinds of noise. I'll describe particular our methods, but I just wanted to say that there has been work, in the past, let's say, 5 years on different kinds of embedding, willing to be robust to noisy TV or in other kinds of noises. All right, so let's start with a simple example here. So let's just consider the action of betting the coin, right? So you toss a coin, I hide it, and then you have to say, okay, is it head or tails? And you win if you were correct, and lose if you were not, right? So you can, the action you take, it's not a coin toss, it's like bet on heads, or bet on the other side. And so you observe the outcome. This is xt plus 1. Either you lost the bet or you win the bet. And so two facts are clear, right? A priori, you could not have predicted this at all, no matter what, right? Because it's random, you don't know what happens. And a posteriori, right, if you lost the bet or win the bet, you can deduce this latent, so what was actually hidden in my hand, a latent fact that the coin must have landed tails, because you know how the game works, right? I just told you how the game works. So this idea we will use in our method. So to be extra clear, if we know how the game works, then in hindsight, the outcome is obvious, right? Either you won or lost the bet. On the other hand, if you don't know how the game works, then you would not be able to predict this infer z, which is kind of this hindsight, nor you would know how to use it to identify the outcome, right? So this suggests that we can measure this understanding of each transition based on how much the outcome makes sense a posteriori. All right, so what we'll try to change in the current definition of curiosity. So we, instead of doing how well we can predict outcome a priori, which is what BioExplorer has been doing, we go to the setting like how we can reconstruct the outcome a posteriori. Because we can have this, for example, we have this trajectory of information, right? So now we'll formalize this using the language of like posterior inference. When the known model of the world is available, but then we generalize to the learned hindsight representation, right? Because we don't know the learned model at the beginning. And when the model of the world is unknown and needs to be learned at the same time, right? So we will have this joint learning. And this gets us to the curiosity of hindsight, which we know that is some kind of approximate optimistic exploration because we'll be upper bounding it, right? So let's be very clear. So I'll let Z be a latent variable that captures all the stochasticity that is there, right? So by construction, the outcome is now deterministic. So the outcome is here, the xt plus 1. So this is our initial state. It could be observation, it could be latent state. Here it doesn't matter. We take the action and we get to the next state, right? So this is what's happening. This is our policy, and the nodes in the circles, in this language, they are stochastic. So since our policy can be stochastic, this is round, and this is all the external noise that it goes to the place, right? So this is a typical structural causal graph with stochastic nodes in the circles and a deterministic node in the squares, and so Z or Z is not observed. And that's why it's not shaded, right? And again, this is just our policy stochasticity. We can just ignore it from hand, right? So in general, the noise is not entirely random. So this is not really completely true, right? So in general, the noise, can influence, can depend on a lot of other things. You can have directed edges coming from X, so the node can depend on the state, it can depend on the action, it can depend on both of them, and also on top of them, it could be some external noise. So different action may induce just different distributions of the noise, and we would like to have a method that be robust to all of that, because that's life, right? Like noise can depend on a lot of things, right? Like for example, in noisy TV, you can change the channel and you have different kinds of noise. Like you can go to the room, we'll have different behaviors of things. Things can move differently, different speeds of elevators, or different random delays of the trains, right? But what we'll try to use, we use this reparameterization lemma that says that there exists, equivalent representation that reparameterize, that it's an equivalent graph under all the node is exogenous, so there is no edges coming into the Z, right? So there always exists such a representation of the thing, maybe not explaining the reality correct, but it's a kind of equivalent representation, and we will use this kind of representation. So now just focusing for one transition for now, let's say we know this graph. So this is not in general true. Let's say somebody have access to that Z, to this external noise. So then, if you know the noise, so if you know what is the noise, or like noisy TV, or the structure of the noise, or even like all the noise samples for forever, then the outcome's entirely deterministic, and so it's learnable with zero error. But of course, we don't have access to Z, and one thing we can do is just to sample from the prior. But this is just the same as predicting the mean of each outcome, right? So this is maybe why you get these blurry pictures in the video completion. And which is what we already know. It's prone to stochastic traps, because you cannot predict the future if you don't know the randomness. It's just impossible. It's ideally, we would like to predict some kind of a distribution rather than specific sample from the randomness. So instead, what we'll do here, and that's a contribution that we have. It's like we sample from the posterior. And so for consistency property of counterfactuals, we know that we can sample any z from the posterior, and it's sufficient from us to recover exactly the true outcome. So in other words, this is coming back to this coin example, condition on this hindsight information, condition what was if you won or lost the bet, the reconstruction error of the true model is 0, if you know the model. So this suggests that if this model is unknown, if f is unknown and learned by the agent, then this reconstruction error is an attractive candidate for an intrinsic reward. So the missing piece in all of this is how to actually sample from this posterior, right? I told you, if you sample from posterior, everything is easy, and you know how to define intrinsic reward, but here it's not clear how to sample from this posterior. All right, so that's what we explore next, and the answer is we will learn some kind of substitute. This is good enough for this exploration without actually having learned to identify the true structural causal model. Right, so we never learn this true causal model. We'll just do something approximate. So we will have a reconstructor f eta that tries to reconstruct the truth, and a generator parameterized by p theta. So these are two networks. So from the generator, you take as an input xt, at, and xt plus 1, and you sample learned z, so you pass it through the generator here, and you sample the learn z, so that's why it is a star, which is if you combine this with the current x and t, so like here I copied x and t up, gets you the back to outcome itself, right? So you try to predict what you already know, but now you don't only try to predict it from the xTNA, from observation and action, but also from this z, which is like a latent variable. And the hope of this will encode the randomness. So, if you know the randomness, then you'll be able to actually well predict the outcome itself. So, maybe one thing I should note is that intrinsic motivation that we use, these are kind of hints what the agent should do, right? Eventually, you would like to maximize some kind of extrinsic reward. And one of the property that we seek of intrinsic motivation, that, for example, if you go to the places and understand the things, then this intrinsic reward should go to 0, right? So one good property that as you keep learning in infinity, it should go to 0. The thing is that when you have these stochastic traps, this could never go to 0 because you can never, predict what you don't know. So at the best, it will not go to 0. It will go to something like entropy of the all randomness that you have. And here, what we'll try to create, by this construction, we'll try to predict an error by, trying to have something that you could predict xt completely. So you'll have something that will go to 0, and something that goes to 0 is a good intrinsic reward. So this is a good property. So that's what we're aiming for, and that's why I'm saying it's good when we can, reconstruct the outcome, completely with 0 error, even with the real model. All right. So our first objective for that is this reconstruction loss. It's just a simple L2 loss, of the agent model for a particular state action. And reconstruction, it will be reconstruction bonus for the agent policy. So in diagram here, the Z star here, refers to the learned Hindsight representation, and unobserved, true latent, that will be learned. Outside of this diagram, we will drop the star because we always, of course, only can work with learned latents because we never have the true one. We always use the learned representation from now on. All right, so if we drive this cost to zero, this reconstruction law says that Z should capture at least all the aspects of dynamics that are unpredictable, such that we don't reward the agents for this for this irreducible error, right? We should not reward the agents for the for the error of the noisy TV. We give it the noise, so it will have to predict it, and it will not get any reward from predicting noise because it's able to predict it. But as you can see, there is there's already some caveat, because we just don't want the Z to say, we don't want to, as we say, leak the information about the outcome that is actually predictable to begin with. For example, we don't want the Z just to copy the outcome, because the Z what could do, it could just take the XT itself and copy the whole thing, and it's just trivially to predict it, right? Like if you get ZT equal to the XT plus 1, so predicting XT plus 1 from XT plus 1 is is trivial, right? And if you just if you set up the problem like that, minimize the error, it will just do that, because it's just simple. It's simple to copy the XT, right? So it's not yet good, interesting motivation. So yeah. So because then the agent would not explore. You just if you predict immediately everything, then you give 0 to your agent. Well, it doesn't know where to go. So our second objective will be independence between the hindsight information and the state and action, right? So we force it to be, independent of state and the action, so it will not be able to copy this thing. So we do this by, critic, parameterized by new, with some kind of, here we use contrastive set of some negative example, so which is some level of invariance nodes. Well, pretty much what we're trying to do, we try to make this ZT independent of state and action. So we have this invariance noise for the agent model and invariance model for the agent policy. So now what are the positive or negative example? We can just sample different state and actions. And so if we drive it to minimize optimality over state and action space, so this critic, it being maximizer and generator being a minimizer. So this is very similar what is done in GANs. So Z now should capture at most. So if you remember the previous loss, the reconstruction loss was to make sure that Z capture at least what is unpredictable. But now Z should capture at most the aspect of dynamics that are unpredictable, right? So you won't like to one loss for at most, one or for at least. So you would like to capture exactly the things that are unpredictable, right? So if you have a noisy TV or random pixels, that should be just that. Yes, so we do reward the agents for this reducible error, and we send it to the agent that has, right? So we have some, I don't go to the details here, but we can verify this reconstruction loss and invariance loss can both to be driven to 0. At the same time, in the limit of this infinite experience. So this suggests that the weighted combination of these two losses is a good intrinsic reward. So now we have these all ingredients for curiosity and hindsight. Now let's make it practical. So first, recall this, vanilla intrinsic reward that we did, for example, with BioExplore, expectation over log of tau. So in particular, we maximize the policy and minimize the error of the model. Here it was, bio loss before. And we try to minimize the loss, and then we send the agents, we maximize the policy. Right, so the model is eta and policy is power. So this is kind of tau eta dynamics, world dynamics being tau. And so what we change now, so the new curiosity and hindsight, so this is the difference from before. I see Eric is standing, so I should finish soon. We define this hindsight in intrinsic reward. which will be the sum of the two rewards, of the reconstruction error and the independence reward, right? So it's we just replace this one curiosity reward with the sum of the two, and both we drive to 0. So this is some kind of upper bound of KL between word dynamics, but I will not go to the details now. So I'll just say that practically this is very easy to implement, because on top of the BIOL that we have, we can just add we can just replace this prediction loss by reconstruction and add additional segment for this invariance loss, right? So we need to replace the predictor that we have with reconstructor, and we just add this part to generate the critic. So it's a simple vanilla modification, doesn't take extra compute. These are simple examples of that. So okay, experiments. We try to make sure that we are robust to all kinds of noise. So first we did experiments on the PyCollab when we have noise like random doors moving, random objects appearing, and we try to go to the different spaces. And on-demand pixel noise when the agent makes an action and gets a noise. And so we showed with the BIOL expert is kind of robust to all this kind of noise, and we measure the number of rooms visited as a sign of exploration. So Brownian oscillators, random pixel noise, and a lot of different things. We also verify that what we get on Atari with sticky action, we keep the performance of BIOL Explorer, and while the BIOL Explorer, vanilla BIOL Explorer, is not able to learn in this case. And I just want to finish with like 1 minute on a little bit on the theory of RL, because it is indeed some kind of magic, and we still try to understand it. So now we focus particularly, I'll have just 3 slides on that. So as I said, BIOL works great, but can we understand it, right? Because in spirit, when you look at BIOL itself, it should already just collapse. So the 2 question is like why BIOL works at all, and what representations should BIOL learn anyway in the case, in particular for RL case. All right. So we are interested in kind of capturing what's happening, and so in particular RL, you can think of capturing something in a transition matrix. So you can do this. In theory, we can solve RL problem, some kind of matrix of the next transition, because then you can easily express value functions, right? So like let's take one step back and think about, classically how one can capture structure of the transition matrix, and the PCA comes to the mind. Is the classic approach to this kind of decomposing covariance and extract principal directions. So here we can think of PCA of principal transition matrix, because this is something that we would like to kind of learn well to decompose dynamics. So I'll just go briefly over that. So we have a paper when we kind of create like a simple model for BIOL for RL that shows that surprisingly BIOL Explorer is kind of doing PCA on this transition matrix. So to show this, we build this simple model for the deep implementation of BIOL. So this is for understanding things better, and BIOL Explorer kind of learns 2 different representations. Like one is representation itself, that's here the phi, and also learns a transition matrix. And so we kind of have one traditional algorithm, one different one. We can show that more formally, we could show that the learning of dynamics of BIOL effectively carries the gradient descent on the PCA on this transition matrix. So this means that BIOL kind of intends to capture more and more information of this transition matrix through this magic of bootstrapping. So So I'll say as much. So this is still a simplified model for tabular MDP in some kind of assumption that, for example, P is symmetric, and so we have kind of dynamics. So now you can also ask how this translates to the origin BIOL. Some of the theory transfer, but there is some kind of intricacies there. So in this paper, I'll put the reference on. We'll focus really mostly on BIOL and theory. So okay, I'll try to have a little big case of RL. So why this RL could be, where it can be still useful. There's any sequence of action that you have, medical health records, games, robotics, business management. As we talked about yesterday, it's still, there's still a lot of difficulties to deal with, and I still invite you to join, research in RL. And one of the more recent discoveries of RL is the discovery of matrix multiplication algorithm using mu0, using the search that was published in Nature by DeepMind 3 months ago. So there's still a lot of discoveries that are happening in RL, and so I still think it's a quite exciting area, and I particularly love it because it studies this kind of closed feedback groups. So I finish with the references of BIOL family. Starting from, there's maybe one I forgot, a world discovery model from like 2018, but then this is stuff that our group, our BIOL team has worked on, including the last 2 papers that are in archive in the last few weeks. Also, thank you very much.
Regularization on or regulation on the sort of curiosity that we would be expecting from an AI, especially in practical or real life scenarios where that might be detrimental for maybe the community or the AI itself.
Yeah, of course, of course you would not like to implement curiosity, in the image of Yann when you go and run car off the cliff. This is something that you can do, or for example here, you can learn the model in simulations and then try to apply it. If you're doing this robotics, there is already a lot of things that you can or you cannot do, right? For example, here, I guess it's like kind of decomposition of the learning of the world model, and then you send it to the in our case, VMPO, which is one of the reinforcement algorithms that we use a lot in DeepMind. For example, in robotics, some actions are just not actionable. You cannot, you cannot have joins that are outside of things. And so already, implementing this in robotics already has some regulations. For example, when we work with robotics teams, they're not able to, do everything that the world model is suggesting, right? So there's some kind of forbidden action, in which case you ignore what's happening practically. Yeah? So this is already in place, and of course you absolutely need to, implement some regulation because some actions you just don't want to take, right? There's a lot of real life system that you don't want to mess with. So yes, absolutely.
So it's hard coded, not.
Yeah. So right now it's hard coded, because you don't want to break the robot as well, right? So.
Yeah. Thank you.
Sure. Yeah.
Thanks again for the 2 speakers. It was very exciting talks. I think so. We have a short break, so very short, 10 minutes, and then we switch back to the continuation of our program, and we try to be there in 10 minutes because we really are a little bit ahead of time already. And so take the advantage of having Yann and Michal to give them questions. And so we'll see you back in 10 minutes.